All right, hello everyone. My name is Dan Liu. I'm an Android developer working out in Trello. So just to give a tiny bit of context, all the examples that are going to be in Java, and then examples of the real world examples going to be in Trello. That's just fine. So welcome to the talk about functional reactive programming. So I've seen a bunch of intro to FRP talks that tend to throw you into the deep end of some reactive framework, and then just confuse the hell out of everyone. And the goal of this talk is to be very simple and to actually get you to understand why people use this in the first place. So I'm going to split this up into two parts because it makes a lot of sense to do it that way. First, talk about what reactive programming is, and then what functional programming is, and then why the two of them work together particularly well. So let's start with the reactive programming side, and with the example that I'm going to keep using over and over and over again, which is an example. The light switch in this case is an observable instance. It's something we can observe the state of, and the light bulb is going to react to whatever happens with the light switch. And so the Java code for that might look something like this, where we create a light bulb instance, and when we create the light bulb instance, we pass a switch to it, and then the switch has some listener that you can observe the state changes on. And so they're pretty much doing exactly the same thing. The light switch changes, and the light bulb turns on. And so then the question becomes, what is really the difference between these two? Why should I care about doing it proactively versus reactively? What's the actual difference between these two methodologies? And by the way, that's all that reactive programming is, by the way. There's all this complicated stuff that people add. That is it at its most basic. So in order to answer the question of why might you want to use one paradigm over the other, I'm going to ask three questions about this. And so the first question is going to be, who controls the light bulb class? So who is actually going out and changing the state of the light bulb? And in the proactive version, it's everyone else is controlling the light bulb. So someone else has to go and ping this power method in order to change the state whether the light bulbs turn on or off. And it's a little weird that everyone else is controlling the light bulb, and also it means that you then have to expose the light bulb's power function to the entire code base, which is a little awkward too. In the reactive setup, who controls the light bulb is actually the light bulb itself. It's the one who figures out whether or not it should be turned on based on the logic of various inputs that it takes. From the flip question is, what determines what the switch controls? So when you change the switch, when you flip the switch, who determines what effects that has? And in the proactive model, it's the switch itself that determines what happens. So in that first code example, we had this switch, and when the onFlip method was called, it would explicitly go out to light bulb and change the state there. Whereas in reactive, the switch itself doesn't actually know what it's affecting. It just has this listener interface that you can plug in, and then whoever wants to plug into it can plug in and then control themselves based on the state of the switch. And so these are kind of inverses of each other. And then the third question I'd like to ask, if the clicker works, is the light bulb synchronous? So as in, is the code inside of light bulb, is it inherently synchronous or is it inherently asynchronous? And I would say that in the proactive case, it's inherently synchronous because you have to call, in the first part, you have to call the power light bulb.power, and then the moment you call that changes what happens with the light bulb. Whereas when you're reactive, it's inherently an asynchronous setup, because what's happening is you're attaching a listener, and you really don't know when the next event's going to be coming into that listener. So it's inherently set up for asynchronous code in that case. Notice I'm not really paying attention to whether the switch itself is synchronous or asynchronous. I'm really much more interested in the light bulb in this example. So what do these three questions mean? What does it mean in terms of the shape of your code? And I think what it really comes down to is one of modularity, and how to create nice modular code that's easy to encapsulate different components and then modify them without affecting each other. And the problem is that in the proactive model, modules control each other. So they have these direct couplings to each other that says, when the light switch changes, go change the light bulb. It's very direct. And that's why I think proactive coding is the way that a lot of people start with, because it's very clear. It's the clear logical thing when you first set up code. But reactive, what's kind of cool about reactive code is that the modules control themselves.
And there's just this glue that's between them that is the listener interface. They can listen to each other, but the light bulb in this case is really controlling its own destiny, and the switch is also controlling its own destiny. They're two separate modules that can be glued together. So let's look at like a real-world example of how this might work. And this is actually the way this code works. So this is like the Trello Android app, and this is the first screen that you see in it. And obviously, you need to get the data for the app from somewhere. So we have this database, which drives all the things that are seen on there. But the question is, again, do we have this proactive model or this reactive model? And if we look at it from the proactive side of things, essentially what we're saying is, when the database changes, also go and update this UI. But then it raises this really good question, is like, why does my database control my UI? Like, does that not seem really strange to anyone else? That when I go say like, oh, the user got added to a new board got created, and I need to go tell the UI about that. Like, that's really weird that I'm going and editing the database, and then immediately thereafter saying, oh, and also check out, see if this screen is being shown, and if this screen is being shown, then also show this new board on it. Like, that, to me, seems like a lot of work, and it seems like very fragile code. Whereas if we switch the arrow around and we say, let's make this reactive, instead what's happening is, whenever the database changes, the UI is notified that the database changes, and it can go and retrieve the new version of the boards. And that, to me, makes a lot more sense, because now the database is completely ignorant of how it's being used directly, so I can make whatever changes I want. I can add boards from 10 different places in the code, and none of them have to know that it's being used on this UI screen. Conversely, the UI screen, it can just operate on its own from any data source. And I can happen to hook in a database. It can listen to it. It could listen to a test data source. It could be anything. I just think this makes the code much more modular and easy to work with. So how do we actually go about implementing this listener stuff? So the first example I had was, let's have this switch that has this onFlip listener interface, and then an add onFlip listener method, which then adds it to some list of listeners, and whenever the flip state changes, then it'll go iterate through all those switches and inform them one by one. So that's a very naive way to do this, the very first pass attempt at it. But the issue, there's a few issues with this setup. One is that every listener becomes unique. So for all the different components in my whole app, then I have to write a new listener for every particular unique event that happens, and that seems just really cumbersome. What I'd really like is for something to be generalizable. The idea of just listening to an event should be something that could be generalized and then build something upon that. And the other thing is that every listener requires direct access to the switch. Because I had this switch add-on-flip listener, I actually have to pass that switch instance around and have people call that method directly in order to start listening to it. And what I'd really like is something that can be passed around. Just the idea of listening to a switch that could be passed around. So how can we create a better object that better represents my desires here? Well, what I really want is to have some method in switch that returns some object that I can pass around and that is much more generalized than this onFlip listener. And so we're going to try to figure out what those 3 question marks are. And there's this great chart that one of the guys who created functional reactive programming gave in a talk, which I'll link later, but I'm kind of stealing it here for this talk. And he said there's basically 4 essential side effects of any function, of what any function returns. And a function is either returning one of something or many of something on one axis. On the other axis, it's either returning that data immediately or it's returning it over time, asynchronously. And so filling this in, if we look at the synchronous one object, that's like the generic type T. So that means it could be a string, it could be an integer, it could be a long, it could be anything, but it's just one single item. Whereas for many synchronous things, you have an iterable. So you could have a list of strings or a list of integers. And in both of these cases, it's synchronous, because the moment you return it from this function, I can go and I can inspect the entire list. There's no time element to that at all. Asynchronously, if you want to return one item asynchronously, what you have is this future. So a future is an object you can return, but it represents data that will come at a future time that you you request that data actually gets processed and returned to you. But so far, we have not quite gotten to what I want yet, because like a light switch, yes, that's something that's going to happen in the future when it gets changed, but it could get changed many times. Like it's going to get flipped up and down and up and down. It's going to change over time. So what I really need is many values over an asynchronous time period. And for that, we have this thing called observable, which is sort of the basis for all of the reactive frameworks that exist out there. And so what observable says is I have many events over time. And so let's say instead, let's plug that in now. Let's say that the switch has this method called flips, which returns an observable of type Boolean. And so this is really cool now because I have this general observable class that just represents a stream of Boolean values. It's no longer directly linked to the idea of listening to a switch. In addition to that, it's something that can be passed around throughout the code. I don't need direct access to the switch anymore. So in my creation method for the light bulb, instead of it taking a switch variable to create itself, it'll take an observable Boolean. And so notice now we have the same type going in and out. And in that code, this code is almost exactly the same as before in terms of adding a flip listener, except for now, instead of adding a flip listener, what we're doing is we're just calling a subscribe method, which says I would like to subscribe to any updates that come through on this observable. So that's an observable. And you notice it's sort of a lot like the observer pattern, which you might have learned about in college or like in design patterns textbooks or something. There's some interesting aspects to observable, which I'm not going to go into too much detail why they are around, but it's worth knowing that there's kind of like 3 key things that happen with observables. And the first thing is what I've been talking about this whole time, which is observing events over time. And the way that observables are often drawn is this diagram called a marble diagram, where that horizontal line represents time's ongoing progression, and then any items on it represent different pieces of data coming through over time. And it turns out that, so let's say for this example that we're streaming data off of Netflix, because Netflix is big into the whole reactive stuff. So we're streaming like whatever favorite Netflix show you have. There's actually then 2 terminal states that you can get into. Like it could just go forever, but all Netflix shows I know of eventually have an ending, and so there's also a way to represent in an observable that the stream of data has ended. So you've gotten all the bytes for that particular video stream. Now that's the end, and that's marked in marble diagrams as a vertical line. But we also need to take into account the fact that things can go wrong and can have errors, which has this X at the end. So imagine that you're streaming your show and then like someone cuts your Ethernet cable or like unplugs the router by accident. That would represent like, we're not going to get any more data, but it didn't end the way we're expecting it to. Like this is an error state for ending, and there's no way for us to continue this stream of data. So that's essentially the groundwork for how reactive programming functions. So any questions on what I've talked about up to this point? Cool. This perfect talk. Or everyone is so befuddled that you can't even imagine raising your hand. All right, so now I'm going to go way off into left field and talk about functional programming for reasons that will become clear later. But this is, you just shove all the reactive stuff out of your mind for a bit, because I'm going to talk about functional programming, which is a completely different concept that doesn't necessarily hook into what reactive does. So when I was writing this talk, I talked to a lot of my friends who are like very into functional programming and was basically like, what do you define functional programming as? And came up with approximately 50 different answers. So this is going to be my version of what I consider functional programming, but please don't like get on my back about it, because there is a lot of different ways to interpret it. But the way that I interpret functional programming is that it's a style of programming built on functions. And by functions, I mean it's a function that has inputs and has outputs. But what I think is really key about functional programming in particular, oh no, something's going on my computer. I know what's going on my computer. Okay, so the real key thing here, though, that distinguishes functional programming from other styles of programming is that we have pure functions as opposed to impure functions. And I'm gonna show you what a pure function is through counterexample. And Java is a wonderful language for showing counterexamples of pure functions. So let's write this really stupid method called add. Let's ignore the fact that the plus operator exists in Java for a bit. This looks like it'll be fine. It's a static function, so everything should be fine. Like it can't access any global state. Like that's essentially what impurity is about, is messing around with things that you didn't mean to mess around with in the function. And as it looks, it just adds 2 numbers. So everything looks good so far. But there's some blank space I left in there. So let's see what's in the blank space. Uh-oh. So this line of code already makes this impure. Because what a pure function does is it takes the inputs and transforms it into the outputs, and then nothing else changes. But this function, in addition to adding these 2 numbers, prints something out to the console. So that's like changing the global state, and you had no idea that this was going to happen from this add function. And then there's another blank line, so let's see what happens from there. It also quits the program. So this is the worst function ever written. But like, from the outside, it looks fine, besides being kind of pointless. But on the inside, it's awful. And so these are side effects, these system.out and system.exit. These are side effects since they suck, because it makes it really hard to program in general. And a lot of what I've been doing in the last few years has been purposely writing code to avoid side effects. Because when side effects occur, it's very hard to like kind of reason about code, to figure out what's going on, because you have to actually dig into everything. Let's look at another side effect. So we're going to have an array, a list of numbers, and we're going to determine whether the sum of those numbers equals the product of those numbers. And so I think that should be true, because 1 plus 2 plus 3 is 6. 1 times 2 times 3 is also 6. So let's look at what our sum method does. It takes our list of numbers, and it's going to iterate through them. It's a little wordy here in order for me to get this kind of contrived side effect in. But it goes through it, it adds them up, and it returns the total. So everything's fine, right? Except for some reason, I added this line of code, probably because this is a contrived example. And if you don't know, if you have an iterator and you call it.remove, it just removes the last thing that it saw through the iterator. So what this sum method actually does is, yes, it returns 6 correctly, but it also took your list input and removed everything from it at the same time. So now this, whether sum equals product, is going to be necessarily false, because sum will get its mitts on it, remove all the items, and then no matter what product does, it's going to end up with an empty list. So again, side effects suck, where I'm changing the parameters that were passed in. And there's really like 4 side effects four hints that you're getting side effects in your functions. These aren't guarantees. You can do side effects on anything. But for example, if there's no input and you're getting an output, clearly a side effect had to have happened. You had to have gone out to some state besides that function in order to get this value. I guess not necessarily. It could be returning a constant, but in most cases, this means that there is a side effect happening. No output. So if I'm consuming food and there's just returning void, what happened there exactly? Like, the meaning of calling this function is necessarily a side effect now. If the output cannot be derived from the input, so this is like, suppose you have a cursor of database query results, and I want to only get the first 5 results, so I have this like get results method. Well, I can't actually figure out what the strings are just from the limit. Like, clearly, again, I'm going out and reaching out somewhere into the ether and getting these results. And then, like the list example I showed, also if it modifies parameters. So this is actually a method in Android where it's like get the hit rectangle for a particular view, and you pass in a rectangle that you want it to modify. So it's like this, in this case, is an intentional side effect, but it is asking for a side effect here. And so things are especially confusing if you change the parameters on people and they don't realize it. So what is functional programming to me? The real key things are pure functions. So all you have is inputs, and they get processed into outputs in a known way, and it doesn't affect anything outside of that function. The second part of that is immutable data. Again, we don't want to pass in a list of integers and have it be modified. We want to know that our parameter that we passed in is going to stay constant throughout time. And then the end result of these 2 kind of like groundwork philosophies is that you end up with needing to use higher order functions to get a lot of things done in functional programming. So what do I mean by that? What is a higher order function? So let's look at this method, which is, for the time being, functional, even though it's in Java. It takes a list of integers, and it goes through and it doubles all of them, and then it returns a new list. So it's not modifying the input list. It's not modifying any state outside of this function, and it returns this output list. So this all seems fine, but it's very, very limiting. It's very inflexible. So like, what if there's all these things that I might want to do with it. Like, what if I want to triple numbers? What if I want to divide numbers? Like, I don't want to have to write a new function for everything I want to do to a list. So let's imagine instead that I have this function interface. And this function interface allows me to transform one integer into another integer. So now I can write this map function. And the map function takes two parameters now. It takes not only my input integer list, but also a mapping function, which transforms those integers into new integers. It's very simple to write. It's pretty much exactly the same as the last thing, except for instead of explicitly calling value times 2, I'm calling this function. And that function will take the input and return the output. And so now I can write code like this, where I've got this list of numbers, and I can double it. And now I can, I is going to I times 2. But now I can stick anything I want in that second function, which is really handy because now I've got the whole world at my fingertips. But not the whole world yet, because right now my example's just been showing integers, but that's really like too limiting in a way. I could go even further and use generics, which I know makes everyone sad, but the generics here, it all works out where I've got a function that can go from one generic type to another generic type. And what this means is that this mapping function now works from one type to any other type. So it'll work for my old example, but it'll also work for something like this, where I've got an array of strings, and then I want to map it to the length of those strings. So I'm taking an array of strings and turning it into an array of lists, or array of integers. So that's really handy. This is especially handy, like I said, in functional programming because we have all these immutable data structures. How do you then convert a list of strings into a list of integers? Within this actual function itself, I'm having a mutable array list. And the answer in functional programming is you have this mapping function, and you just immediately call map, and that way you personally never have to actually modify a list. You're just converting from one list to another. So that's my super quick functional programming introduction. There's way more about that you can learn. But back to reactive land, and why does this matter in reactive programming? Why does people combine functional programming with reactive programming? Let's say that our switch was written slightly differently than before. So our original switch had an observable of booleans. But let's say that we're going to do real over-architecting here and instead have an enum that defines the two different states of our switch, which is on and off. And now what my switch is returning is an observable of states. But my old light bulb code still uses an observable boolean. So now we have a problem, because I can't take my observable of states and just plug it into my observable of boolean. Those are incompatible with each other. But what if I had something that could transform one list of something into another list of something, like that map function I just showed you? That would be amazing. So this is one of the building blocks of how functional reactive programming works, is this map function. So this is a much more complicated marble diagram than I showed before. But essentially, on the top, we have the original timeline. We can consider that a list of states. So that's coming from the switch. Those get passed to a map operator. And that map operator then says, I would like to transform this into something that my light bulb can read. And then on the bottom, we've got what the light bulb sees ultimately. So we can transform a list of states into a list of booleans. And we're doing this through a functional way, where that mapping function doesn't have any weird side effects on the rest of your code. It's just passed in order to do this simple transformation from one type into another. And so the code would look something like this. We have our switch instance, and from it we can get this observable of states. And then that observable class comes along with a map function that you can call. And that mapping function, I'm just going to say that when state is on, then it returns true, otherwise return false. And now I can take that and create my light bulb with it. And so I basically can now take one observable and turn it into any other observable I want. So this is great for data manipulation in general, because if all we had was like a simple observable, you'd be doing all this stuff by hand, and it would be a huge pain in the ass. So it provides all of these operators for you in order to like manipulate data and how data flows through your application. So let's look at another like real world example of that, going back to the Trello home screen. So before I had just like, it is a database providing data to that screen. But it's really a lot more complicated than that. Like it's multiple database tables that are being combined into one in order to be shown to the UI. But there's some timing issues here. So like teams are like, you can be part of many different teams, and then you can have multiple boards inside of each team. But there's a real timing problem here where what if the board's database gets updated first for a new board that's under a new team that just got created as well? If the board database gets updated first, then we have that's getting past the UI, but then it'll say, okay, I want to display myself underneath this team, but the team like doesn't exist yet. So what I really want is to synchronize the two somehow. Like I want to combine the two before any of that data is pushed to the UI. And indeed, such a thing exists, because in Observable, there's this method called combine latest, which essentially says, take the latest piece of data that either of these two streams have passed me and combine them. And so now I can take teams and boards and guarantee that whatever I'm passing to the UI is going to be something that the UI can actually understand. And so the thing that reactive frameworks do is they essentially say, okay, what are all the different ways that you could flow data together? Like this is one example. Another example is mapping data from like the switch to the light bulb. And from that, they come up with like a million different operators. And this is where usually like the other intro to FRP talks blow people's minds, because people get really excited about all these operators. Like, check out what you can do with this and that and the other thing. This is a long learning process to figure out what all of these things do. Like this is just a smattering of the things that people commonly do in reactive code. My advice, if you get into this, is to start with map and then slowly like add one thing on at a time. Don't try to like kill yourself learning all these things at once. So, functional reactive programming. Why is it called functional reactive programming? It's because it is using reactive streams of data. So it's using reactive paradigm, and it is using functional operators in order to transform those streams into something that's useful for you. And that's all it is. The end, basically. Except, why would I want to use any of this stuff? Why am I so into this? For me, there's, again, two different components to it, the reactive and the functional part. The reactive streams gives me that modularity that I like. It's very easy to write different modules where all I'm defining for inputs and outputs are streams of observables, streams of data. And so that's really nice for any given module to just be able to say up front, I'm interested in a stream of Booleans and a stream of like UI combo data object thing that I create. Because that's stuff I was working on yesterday. And for testing, it's really easy. I can just plug in some made up streams. And for development, it's really easy because I just have to figure out where that data is coming from. I don't have to like shape my code so that I explicitly know that this module can talk to this other module. And another thing that's great about reactive streams is that it's inherently asynchronous. And like if you're not, unless you're doing like science calculations in the real world, like things are asynchronous. Like I work on Android apps. Everything in an Android app is asynchronous, whether you like it or not, pretty much. Like you're going to get data over the network. It's going to take some amount of time. The database is going to update. It's going to take some amount of time. It's nice to use a framework that is built around the idea that data is going to come eventually, instead of trying to code things as if it's synchronous and then get really sad when it's not. And then the functional operators. I think functional operators are great because it takes those reactive streams and makes it something that you can actually then like use practically. Because if all you had was the basic observable interface, it would be very impractical to actually use at scale. And then it also is great because the functional operators allow you to like reproduce common logic. Like one of my favorite operators is this one called debounce. And what debounce says is essentially like, so imagine you have, let's see here. It's like a search bar. You're typing on Google. You know how if you type on search, it starts showing you like, here's some suggestions for like how to fill out the rest of your search. Well, as the person's typing, like, do you want to send out a network request every single keystroke they make? Like, that's a lot of network behavior. What you really want is to wait until they've kind of stopped for like a mid-second and a split second, and that's the moment where you want to send out the network request and see what suggestions you want to send back. And what debounce does is essentially that, like in one line of code. So you can say, I would like to get the last event from this stream of data once the stream has like settled for maybe like 50 milliseconds or like 100 milliseconds. And so that's really cool that I can reproduce that common logic anytime I want, anywhere within the code. Again, something I incidentally just used yesterday for some logic. So if you want to learn more, which I'm sure everyone here does now, I wrote a blog post a few years ago about RxJava, which is the kind of mainstream Java implementation of things. This is much more nuts and bolts than what I went over here. This was like high-level overview. That's more like how do you actually use the stuff. There's a really cool framework called Cycle.js, which is predicated entirely, it's another web framework, sorry. That's predicated entirely on reactive streams. And I stole a lot of their explanation for this talk, but I think they are a great framework to look into, especially if you want to learn how reactive coding can like be taken to the absolute limit. Reactive duality, this is a talk from Eric Meyer, who's kind of like the father of functional reactive programming. And that one goes into like the mathematics. Essentially, he takes like a list of T, like a list of items, and he says, if we take this synchronous object and we make it asynchronous, like let's derive the asynchronous version of it, and it turns out that like mathematically, if you derive the asynchronous version of it, you get observable. It's doing that thing again. Sorry. So that one's really mathy, but really, really cool if you want to get into the nuts and bolts of things. And then the last thing is, if you want to learn more functional programming and don't care about the reactive stuff at all, my favorite language for that is Haskell at the moment, because Haskell, like, there's different scales of functional programming. So like some functional programming languages kind of let you cheat, because functional programming is like, if you're doing pure functional programming, it can get really cumbersome after a certain amount of time. Haskell doesn't really let you cheat that much, and so, or at all. So as a result, like if you want to learn functional programming, it's like a really good one because there's no hand-holding here. And this is like a free book online that you can check out that I think is really nifty for learning functional programming. So that's all. Thanks. Oh, wait. Yeah, did people want? Yeah, take pictures. I'll leave this up. Anyways, that's my talk. Let's get pizza.